Good morning, and my name is Dr. Srikar, working as an assistant professor in the Department of Electronics and Communication Engineering. And in last class, we discussed about some introduction to electromagnetic waves and transmission line, which is the current course, and also we discussed some basic concepts in vector algebra, like how to add two vectors, how to separate one vector from the another vector. And in today's class, we are going to discuss about the rest of the topics in vector algebra. So why should we study this vector algebra? This is the question. So this vector algebra is a good mathematical tool which will be very useful in solving different complex problems in electromagnetic waves and transmission line course. So without any delay, let's get into the discussion. So in last class, we discussed about vector addition and vector subtraction. So let's see the position and distance vectors. So what is position? Position defines, suppose let's consider this diagram. And this P is the point in a space, okay, in a three-dimensional space. Since it is a three-dimensional space, we have three coordinates. You can see here 3, 4 and 5. Since it is a three-dimensional space, we have three coordinates. So any point in space is represented by three coordinates, x, y and z. Okay. Suppose this point has coordinates 3, 4 and 5. Means x is equal to 3, y is equal to 4 and z is equal to 5. So what is the position vector of this point? Since I am saying it's a vector, it has some head and tail. So this position vector has its tail at origin and head at point P. You can see here this position vector has its tail at origin and head at P. Now how do we find out this position vector RP? This position vector RP is nothing but P minus Q. P is nothing but 3, 4 and 5. Q is, it's 0, it's not Q. P minus origin. And origin is 0, 0, 0. So 3, 4, 5 is the position vector of this point. That means 3ax plus 4ay plus 5az. This is the position vector of this point. You can see this position vector is directed from origin to the point. Right. Let's see distance vector. So what is a distance vector? Let's consider two different points in space, P and Q. What is the position vector of P? RP. And this one is the origin. What is the position vector of P? RP. And what is the position vector of Q? RQ. Now I consider that distance vector is RPQ. So this one is RPQ, which has its tail at P and head at Q. So from parallelogram rule, I can write that RP plus RPQ is equal to RQ. RP plus RPQ is equal to RQ. RPQ is equal to RQ minus RP. So this distance vector is the displacement from one point to another point. So here the first point is P and the second point is Q. So this distance vector is the displacement from point P to point Q. So here let's consider that the coordinates of point P are xp, yp and zp, and the coordinates of point Q are xq, yq and zq. The distance vector, which is also called as separation vector, is the displacement from point P to point Q as shown in the figure. Right. You can see here RPQ is nothing but RQ minus RP, which is derived here. Okay. And RQ, what is RQ? XQ. What is RQ? XQ, YQ, ZQ. Minus, what is RP? XP, YP, ZP. So which is nothing but XQ minus SP, YQ minus YP, ZQ minus ZP. Then I can write SQ minus XP into AX, YQ minus YP into AY, ZQ minus ZP into EAZ. This is the position vector of, so this is the distance vector or separation vector of 2 points P and Q, and this distance vector is displacement from point P to point Q. So let's solve the problem after shading the definition of position vector and displacement vector. So here we are given two vectors, vector A and vector B. Okay, and we are asked to find out the component of vector A along AY, right or not? So the component of vector A along AY. What is the component of vector A along AY? This vector here has its component along AX, along AY, and along AZ. From this it is known to us. Along AX it has component 10, along AY it has component -4, along AZ it has component 6. Since we are asked to find out the component of A along AY, the component of A along AY is -4, right? And also we are asked to find out the magnitude of 3A minus B. 3A minus B. 3 into 10 comma minus 4 comma 6. These are the components of vector A along X, Y and Z respectively. And these are the components of B along AX, AY and AZ respectively. Okay. And from this we can find out that 3A minus B is nothing but 28 comma minus 13 comma 18. And if you just take the magnitude, you just have to take the square root and square these values and sum those values. That's it. So magnitude of 3A minus B is root of 1277. Similarly, we are asked to find out the unit vector along A plus 2B. And we have already discussed about this unit vector concept in our last class. So first of all, we should find out the vector C. C is nothing but A plus 2B, which can be easily found out from the vector addition. Okay. And what is the unit vector along C? If C is a vector, and what is the unit vector along C? C by mod C. So this is C, and mod C is root of 14 square plus minus 2 square plus 6 square. So unit vector along C is this one. Unit vector along C is this one. And if you calculate the magnitude, you will get 1 for this vector AC. Let's solve another problem. Here we are given 2 points, P and Q. And P is located at 0, 2, 4, and Q is located at -3, 1, 5. And we should calculate the position vector P. So what is position vector P? Position vector P is nothing but 0, 2, 4 means 0AX plus 2AY plus 4AZ. Position vector is 2AY plus 4AZ. Right. And what is the distance vector from P to Q? So this distance vector has its tail at P and head at Q. So RPQ is nothing but RQ minus RP, which has been already seen just now. So RQ is -3, 1, 5, and RP is 0, 2, 4. If you subtract this one from this one, then you will get -3, -1, 1. Then RPQ is -3AX minus AY plus AZ. Since RPQ is a distance vector from P to Q, the distance between P and Q. See, here we are also asked to find the distance between P and Q. So what is the distance between P and Q? Magnitude of the distance vector is the distance between P and Q. So that is what is written here. Since RPQ is a distance vector from P to Q, the distance between P and Q is the magnitude of this vector RPQ. Okay. So distance is equal to mod of RPQ is equal to root of 3 square minus 3 square plus 1 plus minus 1 square plus 1. So which is 3.317. Okay. And also we are asked to find out a vector PQ parallel to PQ with a magnitude of 10. So we should find a vector PQ. So we should find a vector which is parallel to PQ and magnitude of 10. So this is the vector, distance vector from P to Q. RPQ is minus 3AX minus AY plus AZ, right? So now I am going to find out unit vector along RPQ. Minus 3AX minus AY plus AZ divided by root of 3 square plus 1 square plus 1 square. Okay. If I multiply this unit vector along RPQ with magnitude 10 into ARPQ, then I will get 10 by root 11 minus 3AX minus AY plus AZ. See, if you see this vector 10 into ARPQ, this vector has magnitude 10, this vector has magnitude 10, and this vector is parallel to RPQ, right? So this is the answer for the question D, right? So we know how to perform multiplication between two scalars and how to perform multiplication with vectors. So this vector multiplication can be done in two ways. One is scalar product or dot product, and the other one is vector product or cross product. Okay. So when two vectors A and B are multiplied, the result is either a scalar or a vector depending on how they are multiplied. So sometimes when we multiply these two vectors, it gives scalar. Sometimes if we multiply these two vectors, it gives vector. So it depends on how you perform the vector multiplication. That means if you take dot product, then you will get scalar quantity as output. If you take cross product, then you will get vector quantity as output. So here we have seen how to perform multiplication between two vectors. This can be either dot product or cross product. For this, the output is scalar quantity, and for this, the output is vector quantity. Okay. How do we perform multiplication when three vectors are given? So that is the question here. Similarly, here also, the vector multiplication of three vectors A, B and C can result in either scalar triple product or vector triple product. Means the result could be either scalar or vector. It depends on how you perform the vector multiplication of those three vectors. And the vector multiplication of three vectors A, B, C can be done in two ways. And one way is this one, A dot B cross C, and the other way is A cross B cross C. And this one, if you find the output of this one, this is a scalar quantity because B cross C is a vector quantity. Dot product of two vector quantities is a scalar quantity. Whereas in this case, A cross B cross C, B cross C is a vector quantity. Cross product of two vector quantities, that is A and this vector quantity, gives us another vector quantity. So this is a vector quantity. The output is a vector quantity when we perform multiplication in this way, right? So after studying these things, let's look at the definition of dot product. So the dot product of two vectors A and B written as A dot B. So mathematically it is written as A dot B, means dot product of vector A and dot product of vector B, which is not, this is mathematically equal to magnitude of A into magnitude of B into cos of the angle between A and B, right? That means if we have two vectors like this is A and this is B, okay, and this is the angle between A and B, then A dot B is nothing but mod A into mod B into cos of theta AB. Theta AB is the angle between vectors A and B, right? So as I said earlier, theta AB is the smaller angle between A and B, and the result of A dot B is called either the scalar product because it is a scalar, or the dot product due to the dot sign. See, the result of this one A dot B can be called as scalar product because it is a scalar quantity. It can be called as a dot product because this dot symbol is used here. So it can be called in either ways. So no issue. Suppose I have two position vectors and the position vector of A is AX, AY, comma az, means ax into ax plus ay into unit vector along y direction plus az into unit vector along z direction. Then what is the dot product? Dot product of a dot b is ax bx plus ay by plus az bz. Okay. Why is it like that? Here, if you see a bar ax plus ay plus az, and b bar is bx ax plus by plus bz az, right? If you multiply two vectors which are orthogonal to each other or which are perpendicular to each other, then the dot product is 0 because the angle between them is 90 degree, right? That means ax into ax dot ay is 0, ax dot az is 0, ay dot az is 0. So that's why a bar dot b bar is nothing but ax bx plus ay by plus az bz. So that is what is written here. Okay, because ax dot ay is 0, ax dot az is 0, ay dot az is also 0, and this dot product obeys certain laws which are given here. First one is commutative law. Commutative law is a dot b is nothing but b dot a. Okay, so this is well known to us, and this dot product also obeys distributive law. A dot b plus c is nothing but a dot b plus a dot c. And if you perform dot product of two same vectors, it is nothing but the square of the magnitude of that vector, because the angle between the two same vectors is 0. So mod a into mod a bar dot a bar is nothing but mod a bar into cos of theta aa. Cos of theta aa is 0 in this case. That means mod a square cos 0 is 1. So a bar dot a bar is a square. As I said earlier, vector multiplication can be done in two ways. One is dot product and another one is dot cross product. And we have already seen how to perform dot product when two vectors are given. Now let's see how to perform this cross product multiplication when two vectors are given. The cross product of two vectors a and b, written as a cross b, is a vector quantity whose magnitude is the area of the parallelogram formed by a and b, and is in the direction of the advance of a right-handed screw as a is termed into b. So what does this physically mean? Suppose I have two vectors, and this one is a bar and this one is b bar. So what is the magnitude of a bar cross b bar here? According to the definition, it is the area of the parallelogram formed by a and b. So here we should form a parallelogram here. This one is b bar and this is the vector which is parallel to a. If you calculate this area is nothing but magnitude of a bar plus b bar. Since the result is a vector quantity, it has some direction. So what is the direction? Suppose there is a screw, right-handed screw. That means if we move from A to B, the screw goes upwards, right or not? If you move from A to B, so these two vectors are in one surface. Okay. If you move from A to B, then the screw moves upwards. If you rotate the screw in such a way that it grows from A to B, then that screw automatically goes upward. Means the direction is normal to the plane containing A and B. So that's why here AN is given. Means this is the vector which is perpendicular to the plane containing A and B. This is a unit vector which is perpendicular to the plane containing A and B. So let's look at the thing A cross B mathematically. A cross B is nothing but mod A into mod B, mod A into mod B, sine of theta AB into AN. AN is a unit vector which is perpendicular to the plane containing A and B, right? See, here we are given two vectors. A is equal to AX plus AY plus AZ, and B is equal to BX AX plus BY and BZ. And how to find cross product of these two vectors? Okay, you just have to perform the cross product in this way: modulus of AX AY AZ, BX capital AX capital AY capital AZ, BX BY BZ, and AX into AY minus BZ. Sorry, AX into AY BZ minus AZ BY, and minus AY into AX BZ minus AZ BX plus AZ into AX BY minus AY BX. So this is the result of this. This is the result of this cross product of two vectors A and B, right? And this cross product can be obtained by crossing the terms in cyclic permutation. Hence the name cross product has come here. So what is this cyclic permutation? See, let's see. AX, AY, AZ. This is the unit vector along x-axis, and this is the unit vector along y-axis, and this is the unit vector along z-axis. Cyclic permutation. If I move from AX to AY, that means answer is AZ, which is nothing but AX cross AY. If I move from AY to AZ, that means AY cross AZ, which is nothing but AX. Here AZ to AX, that which is nothing but AY. If I go in reverse direction, that means here this is minus AY, this one is minus AX, and this one is minus AZ. That is what is drawn here, right? Moving clockwise leads to positive results. Moving counterclockwise leads to negative results. When we move clockwise direction, it leads to positive results. When we move in anti-clockwise direction, it leads to negative results, right? The cross product has the following basic properties. It is not commutative, it is anti-commutative. It is anti-commutative. That means A cross B is not equal to B cross A. A cross B is not equal to B cross A. So that's why it is anti-commutative. Whereas dot product obeys commutative property. Here it doesn't obey commutative property. And also it is not associative, because A cross of B cross C is not equal to A cross B cross C. Okay. See, it can be easily cross-checked or verified. See, if A is AX, B is AY, and C is AZ. This one is AX, this one is AY, and this one is AZ. So what is AY cross AZ? AY cross AZ is AX. So which is equal to 0, right? And here, in this case, you may get both the things same. But if you take some complex vector like 3ax plus 2ay as A, and 2ax plus ay as B, and ax plus 2ay as C, then you will get to know easily. Okay. So it doesn't obey commutative property, and it doesn't obey associative property as well. However, it obeys distributive property. right? That means A cross of B plus C is nothing but A cross B plus A cross C. And what is the result of A cross A? If we take the cross product of two vectors, the result is 0 because A cross A is nothing but mod A into cos of angle, sine of angle theta AA. Here theta AA is 0. Sine 0 is 0. So mod A square into 0. Answer is 0. So cross product of two same vectors is always 0. So as we saw earlier, AX cross AY is AZ, AY cross AZ is AX, and AZ cross AX is AY, right? How do we perform this? Scalar triple product means when three vectors are given, how do you perform this multiplication on these vectors? As I said, it can be done in two ways. One is scalar triple product, another one is vector triple product. If we do in this way, A dot B cross C, then you will get scalar quantity as your output because this is a vector and the result of these two things is a vector. Dot product of two vectors is a scalar quantity. And A dot B cross C is nothing but B dot C cross A, which is also equal to C dot A cross B. This is an identity, okay, which can be obtained in cyclic permutation. And what is the area of this result? So I mean, what is the scalar quantity? What is the magnitude of this result? It is nothing but the volume of the parallelogram formed by A, B, and C as edges. And it can be easily obtained by finding the determinant of 3 cross 3 matrix. So if we take the different determinant of this 3 cross 3 matrix, this is nothing but the volume of the parallelogram formed by edges A, B, and C. Means this is the output of the vector multiplication A dot B cross C. Okay. Since the result of the vector multiplication is a scalar, it is called the scalar triple product. Right. Now, this matrix multiplication can be performed in another way also. So, if you are given three vectors A, B, and C, and if you want to perform multiplication in such a way that the output is a vector quantity, then you should do multiplication in this way: A cross of B cross C, because B cross C is a vector quantity, and vector quantity of two vector quantities is always a vector quantity, and this is equal to B. This is equal to B into A cross C, A dot C minus C into A dot B. This is called as back cab rule. BAC back, CAB cab. This is called as back cab rule. And it should be known that A into B into C is not equal to A into B dot C. But AB into C is nothing but is equal to C into AB. These two terms can be interchanged. Okay, but these two terms cannot be equal. Right? Components of a vector. So this is one of the topics which is very important in this course. And sometimes we should find out the vector component of one vector along another vector to make the mathematics simple. Mathematical calculation simple. Okay. So here we have two vectors, vector A and vector B. So here vector A and vector B. This is vector B and this is vector B. What is the vector component? What is the component of A along B? And this is theta AB. If I draw projection from A to B, from here to here, this is nothing but the component of A bar along B bar. And this one is nothing but AB. Okay. If I want to find out the vector component, then what should I do? I just have to multiply with the unit vector along B. That means A dot B is equal to A into AB. So how do we get this one? That's the question now. Right? See, this is a right angle triangle. This A and this projection and this component. This A, this projection and the component. Right? And this is A bar and this is theta AB. And this component AB is nothing but A bar into cos of theta AB. This is the component. This is the component of vector A along B. A bar cos of theta AB. And this can be written like this. Mod A bar into mod AB. This is unit vector along vector B and cos of theta AB. Because mod of AB is nothing but 1. Okay. So that is what is written here. But here it is a scalar quantity because it is a scalar, and it is a scalar. It is a scalar quantity. But if we want to find out the vector component, then what should we do? We just have to multiply with AB, which is the unit vector along B. That's it. Sorry, this one. We just have to multiply with AB, which is the unit vector along B. AB into B, which is nothing but AB dot AB into B. Okay. See, here you can see this is your vector A and this is your vector B. Theta is the angle between these two vectors A and B, and AB is the scalar component of vector A along B, and this AB is the vector component of vector A along B. And since it is AB, this vector is A minus AB, because AB plus A minus AB is equal to A. Right? So A gives us the scalar component of A along vector B, and B gives us the vector component of A along vector B. So from figure P, the vector can be resolved into two orthogonal components. One component is AB, which is parallel to B, and the other component is A minus AB, which is perpendicular to B. So from this knowledge, let's solve one more problem. We have been given two vectors A and B. We just have to find out the angle between two vectors. So you can find out the angle between two vectors from either dot product or cross product. So from dot product, here the angle between two vectors is found out. Okay, we just have to take the magnitude of B and take the magnitude of B and apply this formula. Cos of theta AB is nothing but dot product of vector A and vector B divided by magnitude of A into magnitude of B. Okay. And alternatively, theta AB is nothing but cos inverse of this value. So it gives answer as 83.73 degree. Means this is the angle between A and B. Similarly, from cross product also we can find the angle between A and B. Sin of theta AB is nothing but mod of A cross B divided by mod A into mod B. Mod A and mod B are already calculated. And what is the magnitude of A cross B? It can be calculated from this. Okay. And this magnitude is root of 745. Root of 745 divided by root of 26 into root of 29. So this is the value of sin theta AB. And this theta AB is nothing but sin inverse of this value, which is 83.73. See, you get the same answer in both the ways. If you get different answers, then it means that you have done some, your calculation is wrong somewhere. So till now we have shared about vectors, means how to add two vectors, how to separate one vector from another vector, and how to find the position vector, and also how to find the distance vector. Okay, and how to perform multiplication on two vectors or multiplication of three vectors. Okay, and after studying these things, let's look at coordinate systems and transformation. So here, why do we study coordinate systems here? Because throughout this course, you will be performing some mathematical analysis using these coordinate systems only. So generally, we have three types of coordinate systems. One is Cartesian coordinate system or rectangular coordinate system, and the other one is cylindrical coordinate system or spherical cylindrical coordinate system, and the third one is spherical coordinate systems. Sometimes we get we get results easily when we use cylindrical coordinate system. Sometimes we get results easily, means we can derive the things easily using spherical coordinate system. Sometimes we can derive the things easily using Cartesian coordinate system. So depending on the type of the problem, you should choose which coordinate system is the best fit. Okay. So a point or a vector can be represented in any curvilinear coordinate system. This curvilinear system is nothing but a coordinate system which may be orthogonal or non-orthogonal. So an orthogonal coordinate system is one in which the coordinates are mutually perpendicular. Okay. If the coordinates are mutually perpendicular, then I can term that one as a orthogonal coordinate system. See this Cartesian coordinate system. This is an example of orthogonal coordinate system, right? So if I have a point P, in space, then according to Cartesian coordinate system, its coordinates are x, y, and z. Okay. And what are the dimensions of this value? What are the dimensions of x, y, and z? X can be any value between minus infinity and infinity, and also y can be any value between minus infinity and infinity, and z can be any value between minus infinity and plus infinity. Okay. So these are the coordinates of point A, ax, ay, ay. And what is the position vector of A? Ax, ax plus ay, ay plus az, az. So if I have coordinates like this is x, and this is y, and this is z. This z is coming out of the plane containing x and y, and this is the unit vector along x-axis, and this is the unit vector along y-axis, and this is the unit vector along z-axis. So any point in space with respect to Cartesian coordinate system, so any position vector in this space with respect to Cartesian coordinate system can be represented like this. Components along ax, ay, and az. So where ax and ay and az are the unit vectors along x, y, and z directions. So let's look at the another coordinate system, which is cylindrical coordinate system. This is not circular. Cylindrical coordinate system. See, if you take cylinder, it is a three-dimensional object, right or not? It is a three-dimensional object. So if you want to find the coordinates of any point in the three-dimensional object, it should have three coordinates since it is a 3D structure. 2D, then 2 coordinates. 3D, then 3 coordinates. So that's why we have here 3 coordinates, rho, phi, z. So why do we have rho, phi, and z here? That is a question here. Okay. So let's take a ring first. This ring has some radius. Let's just assume that the radius of that ring is rho. Okay. This ring has some radius. If I consider only that rho, this center as the reference position. If I consider that only one coordinate is there, then this is rho, and this is also rho. This is one. Everywhere on the circle, the point is just rho. But we know that no two points in space can have all the coordinates same. So that's why we need one more coordinate, that is phi here. See, from here to here, you should make 360 degrees angle rotation. That means if it is 0 degree here, it is 90 degree here, and it is 270 degree here, and it is 360 degree here. Now every point on this ring has unique coordinates. At least one of those coordinates is different from the other points coordinates, right? This is rho, 360 degree. This is rho, 270 degree, right? So if I place one more ring on this ring, if I keep placing similar rings, then you will get a cylinder, right? Then if you take bottommost ring and the topmost ring, and if you again consider these coordinates, then also on the bottommost ring, this point has rho, 0 degree, and at similar point on the topmost ring, it has coordinates rho, 0 degree. But according to the definition, no two points in space can have all the coordinates same. So that's why we should introduce another coordinate which is called as z. Okay. So this is the topmost ring and this is the bottommost ring. Okay. And this one is rho comma 0 degree, and this one is also this one is rho comma 0 degree, and this one is also rho comma 0 degree. If I introduce some other dimension called z axis, called z, then this one is z is equal to 0. If I say this one is some z. Now if you take any point on any two circles, if you take any 2 points on any two circles, one point in one circle, another point on another circle, then at least one of the coordinates must be different from the other coordinates. So that's why we need 3 coordinates in cylindrical coordinate system. And here we have unit vectors along rho direction, unit vectors along rho axis, along phi axis, and along z axis. How do we get these directions? That is the another question here. Right. See, let's take one ring. Let's take another ring. This one has rho 1, rho 2, rho 3. This is rho axis. This is also 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 rho axis. Because on rho axis we have increasing values of rho. In Cartesian coordinate system also, on x axis we have increasing values of x. On y axis we have increasing values of y. On z axis we have increasing values of z. So my arrow direction will be also in the increasing values of rho. Okay, so that's why here you can see this rho. If I take another cylinder here, this is A rho. And how will be the direction of A phi? That is the question here. See, if you take one circle, this is phi is equal to 0, this is phi is equal to 90, and this is phi is equal to 270. This is phi is equal to 360. Sorry, this is phi is equal to 180, and this is phi is equal to 270. Previously also this is phi is equal to 180, 270, and again 360. Okay. If we go in clockwise direction, anti-clockwise direction, we have increasing values of phi. So my A phi direction should be in such a way that it should be along increasing values of psi. So at this point, the A psi direction is like this. At this point, A psi direction is like this. At this point, A psi direction is like this. At this point, A psi direction is like this. So that's why here, at this point, A psi direction is like this. And when it comes to z axis, Az. If we go in this direction, then we have increasing values of z. So that's why Az's direction is like this. See, you can see here, Az pointing upwards. Here we have variables, coordinates, rho, phi, and z. Then what are the ranges of rho, phi, and z? Rho can be any value between 0 and infinity, because rho cannot be negative since it is a radius. And phi can be any value between 0 to 360 degree or 2 pi if it is radian. And z can be any value between minus infinity and infinity. From cylindrical coordinate system we know this. Okay. And how do we represent a vector A in cylindrical coordinate system? It is represented in this way. A phi, arrow, capital A phi, capital Az, Az. Okay. How do we find the magnitude? We just have to take the squares of those components and sum those things and take the square root of the quantity. Here also we should follow circular permutation. Dot product of two same vectors is always 2 unit vectors is always 1. two unit vectors which are in same direction. That's why it is 1. Here angle between psi and aero and a phi is 90. Here also angle between aero and az is 90. Here also angle between az and aero is 90. That's why the quantity is 0. The output quantity is 0. And here also aero, a phi, az. Cyclic permutation. From here to here, from here to here. Aero cross a phi is az. And a phi cross az is aero. And az cross aero is a phi. Okay. Now we define some relationship between Cartesian coordinates and cylindrical coordinates. So these are the relations between Cartesian coordinates and cylindrical coordinates. How do we find this? See, let's take this one. Let's consider that this is the radius. This is the radius of the cylinder rho. So at this point, so this is your x-axis and this is your y-axis. Okay. This is some point on the cylinder. According to Cartesian coordinate system, it has coordinates x, y, z. According to cylindrical coordinate system, it has coordinates some rho, phi, z. So this is your x-axis, and this is my x component x, and this is my y component y. Okay, and this is the angle phi made from x-axis. So this is psi, and this is rho, and the component of rho along x-axis is x is equal to rho cos phi, and this is psi, and this is 90 minus psi, and the component of rho along y-axis is rho cos of 90 minus psi, which is nothing but rho sin phi. So actually it is rho sin phi. From this I can say that rho square is equal to x square plus y square. Rho is equal to root of x square plus y square, and z is simply z, right? And from these two equations 1 and 2, I can say that if I do 2 by 1, then tan phi is equal to y by x. Phi is equal to tan inverse of y by x. That's it. So another coordinate system is spherical coordinate system. If you take any sphere, it is a three-dimensional object. If you want to represent any point on that sphere, then it should be represented with 3 coordinates, and those 3 coordinates are r, theta, and phi. So why should we have r, theta, and phi here? That is a question here. Okay. See, if you take some sphere, it has some radius, right? So that's why it has coordinate r. Okay. See, you must have studied about cone. This is axis, and this is angle theta, and this is angle theta. Instead of cone, if I make this surface like this, if I keep increasing this angle theta, at one point of time, I will get a structure like this, 3D object, semi-sphere. When will I get that object? If theta is 90. If theta is 90. If theta becomes 180, then I will get full sphere. That means the range of theta is between 0 and 180. And what is the range of r? Between 0 and infinity. Because radius of the sphere can be anything which is less than infinity, and it can't be negative, right? And from our previous coordinate system, we already know the range of psi. Okay, range of psi is 0 to 2 pi, theta is 0 to 180, r is 0 to infinity. This is we represent a vector in a cylindrical coordinate system. Where A, theta, and A phi are the unit vectors along r, theta, and psi. Here also, if you take any two unit vectors along a different axis, then they are perpendicular to each other. This is how we should find out the magnitude of A. Here also again cyclic permutation. And if Cartesian coordinates are known, how do we find out spherical coordinates? From this we can find out From these relations, we can find out spherical coordinates. Okay. We already know that x is equal to rho cos phi, x is equal to rho cos phi, and y is equal to rho sin phi. Here, we should find what this rho is in terms of r and theta. So this is r. So if I take any sphere like this, from center of the sphere to here is radius, and this one is theta, and this one is 90 minus theta. So r cos of 90 minus theta is rho. Rho is equal to r sin theta. So that's why here r sin theta cos phi, r sin theta sin phi. Z is equal to r cos theta. From these three equations, we can get these things. Clear? Next, transformations. Suppose if ax, ay, and az are known, we have to find out a phi equivalent a phi, a rho, a phi, az. And this is how we should find the cylindrical coordinates. If cylindrical coordinates are known, then how do we find out Cartesian coordinates? From this, we can find out easily. We just have to take the component vectors. That means ax should be represented in terms of a phi, a rho, a phi, and az. Then you will get this matrix. That's it. Similarly, if Cartesian coordinates are known, then how do we find out spherical coordinates? In this way. If spherical coordinates are known, then how do we find out Cartesian coordinates? In this way. See, let's see the coordinate systems and transformation. And this is a x constant plane, and this one is a y, z is equal to constant plane, and this one is y is equal to constant plane. X is equal to constant plane means at any point x is constant. Y is equal to constant means at any point y is constant. See, as we know already from this, z is equal to constant plane is this. Then how is r is equal to constant plane? R is equal to constant plane is nothing but a cylinder. If you take any point on the cylinder with reference to central axis, its radius is constant. So r is equal to constant plane is a cylinder. Then how is phi is equal to constant plane? Phi is equal to constant plane is a semi-infinite plane, because 0 to 360, right? Psi, semi-infinite plane, because psi is equal to constant plane has its normal. Suppose if I take this plane, this is a phi. So psi is equal to constant plane is a semi-infinite plane. How is r is equal to constant plane spherical coordinate system? It is just a sphere. Theta is equal to constant semi-infinite plane, as we know already from this cylindrical coordinate system. And theta is equal to phi is equal to constant, and theta is equal to constant is a conical surface. If you take any point on the conical surface, the angle that make with this z-axis is constant. So let's look at the differential length, the differential area, and differential volume. Length is always considered as a scalar quantity in this course, and surface is also considered as a length is considered as a vector quantity in this course, and surface is also considered as a vector quantity. Volume is considered as a scalar quantity. So if we take any differential displacement, see this is in yz plane. So that's why dy dz into x cap. This one is in xz plane. That's why dx dz into y cap. So these are the equations for differential displacement, differential area, and differential volume in spherical coordinates. In cylindrical coordinates. These are the equations in spherical coordinates. So it can be easily found out from the shortcut also. See, instead of remembering 9 equations here, if you know the scaling factors, then you can use these formulas to find out dl, ds, and dv. Okay. Suppose if I take spherical coordinate system, then dv is nothing but h1 into h2 into h3 du dv. That means h1 is 1 into r sin theta. Du is dr d theta d phi. That means r square sin theta dr d theta d psi. This is dv in spherical coordinate system. R square sin theta dr d theta d phi. So we can find out from this shortcut. Next comes line, surface, and volume integrals. This is how we perform a line integral. This is how we perform a surface integral, and this is how we should perform a volume integral. And there is one mathematical operator called del operator, and we can use this operator on a scalar quantity to get a vector function, and it can be also performed on a vector quantity in these three ways. Means del dot A, divergence of that vector, del cross A, curl of that vector, del square A, Laplacian. See here also there are different equations. This is del operator when it is operated on a scalar, and this is gradient operator. This is when this del is operated on a vector, and this is divergence. Divergence is nothing but the outward flux. Suppose at this point, what is divergence? Suppose if I consider the point, divergence at a point is nothing but the outward flux crossing through some area as this volume shrinks about P. Okay. Suppose if I consider point like this, if the fields are like this, then I can say it is a source point. Means the field is divergence. It has positive divergence. If the fields are like this, then I can say it is convergent. That means it has negative divergence. This has positive divergence. Suppose the fields are like this, and this is my point where I want to find out divergence. Then the divergence at this point is 0, because number of fields diverging is equal to number of fields converging. And how do we find the curl of a vector? Suppose there is a point, and this vector A is in this direction. Curl means circulation. So this about this point, this has some circulation. Okay. Suppose if vector is like this, then there is no circulation. So curl of the vector is nothing but axial vector. Axial vector means nothing but rotational vector whose magnitude is the maximum circulation of A per unit area as area tends to 0, and whose direction is normal to the direction, and whose direction is the normal direction of the area when the area is oriented to make the circulation maximum. Right. Where delta S is the area bounded by the curve, A n is the unit vector normal to the surface delta S. Right. And from these formulas we can find out the curl of a vector. And here also with these shortcuts we can find out divergence, curl of a vector, and del of scalar, gradient of a scalar. If you just remember these scaling factors, you can get these things for any coordinate system. Okay. And what is let's look at Gauss divergence theorem. See here I am not going to give proof for this theorem. You just remember that the surface integral of a vector is nothing but the volume divergence of volume integral of the vector. That means the total outward flux of a vector field A through the closed surface is same as the volume integral of the divergence of A. Similarly, if you see Stokes' theorem, line integral of a vector is nothing but the surface integral of curl of that vector. It states that the circulation of a vector field A along a closed path. This is the closed path. Okay. And if there is some vector A, which is continuous on X, this is the surface, if there is some vector A which is continuous on S, then the circulation of vector A around the closed path, is equal to the surface integral of curl of A over the open surface. This is ds bounded by L, provided A and del cross A are continuous on S. This is what is called as Stokes' theorem. Line integral is equal to surface integral. Line integral of a vector is equal to surface integral of curl of that vector. Here, surface integral of a vector is nothing but divergence of volume integral of divergence of that vector. Right. So these are the references. We have just followed the textbook. Elements of electromagnetics by Srikar, extension, Oxford University Press. So all these things have been taken from this textbook. So with this, we have completed the introduction part of the course EMTL, and we have also seen some mathematical tools in vector algebra. From next class, we are going to start module 1. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.